All right, let's just dive straight into this explainer. Today, we're going to absolutely master SQL data modification. And we're also going to uncover something pretty fascinating, the hidden cost of indexes. You see, if you're working with databases, you really need to understand not just how to change your data, but what those changes actually do to your system's overall performance. So we're going to break this all down logically, step by step, so that you walk away with a complete, crystal clear understanding.
It's kind of a terrifying thought, right? You sit in there, you press enter, and suddenly realize you just accidentally deleted an entire database. Well, today, we're exploring the high-stakes, real world of data manipulation, where those kinds of massive disasters are, quite literally, just one missed keystroke away. But don't worry. By the end of our time together, you won't just know how to manipulate data safely and confidently, you'll also deeply understand the secret, under-the-hood performance costs that end up catching so many database administrators completely off guard.
To kick things off, we need to talk about DDL versus DML. The easiest way to grasp this? Think of DDL, or Data Definition Language, as building the actual house. It's the permanent structure. DML, or Data Manipulation Language, on the other hand, is like moving the furniture around. It's what changes the data inside those existing tables. And our entire focus today is purely on moving that furniture, the DML. The overall structure of the table is going to stay exactly the same, but the records, the actual contents, are what we're changing. So let's map out the big three DML commands we're going to be tackling today. If you're changing data, you're almost certainly using one of these. First up, insert, which adds a completely new row. Second, update, which edits a row that's already there. And third, delete, which simply removes a row. All three of these are the core of SQL data manipulation, because they work directly with the contents of your existing tables.
Section 1. Adding new rows with insert. To make this really concrete, let's just follow the life cycle of a single piece of data. Imagine our database is for school, and we need to welcome a brand new student into our system. We'd use this exact syntax. Insert into students, then in parentheses, student ID, name, year group, followed by values, and then 101, Mina, and 12. So we explicitly specify the table, students, list the columns, and then provide the exact corresponding values. Boom. This creates a brand new record for Mina, placing her right into the database without altering the actual table design in any way.
But you know, there are some pretty strict rules to this whole thing. Let's quickly review the best practices. You should always list your column names clearly so your values go into the exact right fields. Make sure your values perfectly match the field data types. Please do not try to put text into a number field. It won't end well. Crucially, your primary key values, like Mina's unique student ID of 101, they have to be absolutely unique. And never skip required values, or your statement might just fail completely and reject the new row altogether.
Section 2. Modifying existing data.
Okay, so time passes. Our student Mina moves up a grade, and her record needs an edit. Now, we obviously don't want to create a brand new Mina, we just need to update her current reality. Here's the syntax for that. Update students, set year group equals 13, where student ID equals 101. We use update to target the students table, set to change her year group from 12 to 13, and honestly, this is the most important part. We use the where clause to make absolutely sure we uniquely identify her row using her student ID. The row stays right where it is, just with newly updated information.
And that brings me to this. Without a where clause, an update changes every row in the table. Literally let that sink in for a second. If we just forgot to type where student ID equals 101, we wouldn't have just moved Mina to year 13. Nope, we would have accidentally changed the whole school's grade all at once. Every single student from year 7 to 12 would suddenly be in year 13. It's a complete catastrophe, and it's born from just one simple typo. Section 3. Removing existing data. Well, we've reached the end of Mina's data life cycle. She successfully graduated and now needs to be removed from the active system. The syntax you need is right here. Delete from students where student ID equals 101. The selected row is wiped out entirely, but the table itself, it's still there, holding all the other active students. But just like with the update command, I have to urgently warn you, missing that where clause will wipe out all the rows in your entire table. Always double check your conditions before deleting, because getting those deleted rows back, yeah, that can be a massive headache.
Now, to make sure you're using the right tool for the job, let's quickly compare the different levels of destruction here. If you just want to remove one specific canceled booking or one graduated student, use delete.
But what if you want to empty every single row, but keep the actual table structure intact for future use? That's truncate table. And if you want to go nuclear and completely remove the table design from existence entirely, that's drop table. Definitely know the difference between these three.
Okay, so here is the major plot twist. What actually happens behind the scenes when you change thousands of rows at once? We've mastered the basic SQL syntax for just one student, but now we need to pivot. We really need to look at the advanced system architecture and all the hidden administrative paperwork that databases are forced to perform every single time you run those DML commands at a large scale.
Section 4. The hidden cost of indexes. Think of an index exactly like the index at the back of a massive textbook. It's incredibly fantastic for searching, right? But it sets up a huge trade-off: faster searches versus slower updates. Read-heavy systems absolutely love indexes because lightning-fast searches really matter. But when you insert, change, or delete an indexed value, all those extra index structures, they have to be updated too. Because of this, heavy insert, update, and delete write activity slows down drastically compared to non-indexed columns, purely because of all this extra write work.
Let's break down this hidden workload. I actually like to call this the index maintenance tax. When you run an insert, your database literally has to add a new entry into each and every relevant index. What if you run an update on an indexed column? Well, the database has to remove the old index value and then insert a brand new one. And a delete? The index entry must be removed entirely. The core takeaway here is super simple but crucial. The more indexes a table has, the more maintenance every single data change is going to require.
Section 5. Post-modification index maintenance. Because here's the thing. After massive data changes, your index pages get completely scattered and fragmented, which severely reduces your database's efficiency. You basically have two main upkeep strategies to fix this mess. Reorganize tidies up the existing index. It's lighter maintenance and it's perfect for moderate fragmentation or just your routine upkeep. Rebuild, on the other hand, creates a totally clean slate from scratch. It's absolutely necessary for heavy fragmentation or after really large data modifications. But be warned, rebuilding consumes heavy system resources and takes significant time, so it really has to be planned out carefully by the administrator.
All right, before we wrap up, let's just quickly review some shortcuts to really lock in these system architecture best practices. Remember, insert equals add, update equals edit, and delete equals remove. Those are your core DML commands. And always remember the golden rule of database architecture. Indexes heavily help your reads, but they add significant write overhead.
I want to leave you with one final, kind of provocative thought here. Indexes speed up the reads, sure, but are you prepared to pay the price on the writes? You really have to start thinking like a true database administrator. Every single architectural choice is a trade-off. Next time you build a table or write an update statement, I want you to ask yourself what that action is really costing you behind the scenes. Thanks so much for joining me on this explainer, and keep learning.